From the primordial cloud of gas and cosmic dust, gravity forged the stars. Gravity connects star systems together in vast galaxies and steers them on their journey through unbounded space. The relentless flow of time has driven the evolution of the universe and created extraordinary wonders. Some galaxies form so close together that they're locked in a gravitational embrace. What a magnificent sight it would be. As it evolves, the universe passes through distinct eras. Vast ages whose beginnings and endings are marked by unique milestones. The births and deaths of its wonders.
We are the product of a grand evolutionary sequence, cosmic evolution, about which we are only occasionally aware.
Gravity is the great creator, the constructor of worlds. But gravity is also the destroyer, because it's relentless. When a star around 15 times the mass of our Sun collapses, all the matter in its core is crushed into an infinite void of blackness known as a stellar mass black hole. The immense gravitational pull of these monsters can rip a star apart. They tear matter from its surface and drag it into orbit. This superheated matter spins around the mouth of the black hole, and great jets of radiation fire from the core. Although these jets can be seen across the cosmos, the core itself remains a mystery. Not even light can escape, so their interior is forever hidden from us. Throughout a star's life, there is a constant battle between energy pushing out and gravity pushing in. When it runs out of fuel, the star collapses and then explodes with the brightness of 1 billion suns. As the star is torn apart, it will fire out into space all the elements that it created in its life and death. These are new stars forming from the elements blown out by supernova explosions. New stars being born from the remains of dead ones. And it's from this universal process of death and rebirth that we emerged. Because it was in a nebula just like this, 5 billion years ago, that our sun was formed. Clouds of hydrogen collapse further and further under the force of gravity, and the life cycle of a new star has begun. A star was born that would come to be known as the Sun. Around it, a network of planets formed. Among them was the Earth. Debris left over from the formation of the solar system collides with the Earth. Earth began life as a molten hell.
The early continents were still forming. The land was dominated by volcanoes, hostile and lifeless. But deep in the oceans, life had begun. The latest theory is that chemicals spewing from underwater volcanic vents solidified and created the conditions needed for the first cells to form. For some 3 billion years, simple microscopic organisms were the most advanced form of life on the planet. Cyanobacteria and other oxygen-producing microbes began to bloom. These flourished in colonies of plant-like microbes that pumped out enormous volumes of oxygen. And it was this increase in oxygen that was the key to the rise of the animal kingdom.
Organisms started using oxygen to respire, yielding a lot more energy, which allowed the development of more complex life.
Just before complex life appeared, the world was in the grip of the biggest ice age in its entire history. And then suddenly, advanced organisms appeared. Holocene has ended. What we do now and in the next few years will profoundly affect the next few thousand years. The only conditions modern humans have ever known so far are changing, and changing fast.
Nothing stays the same on this planet. Everything changes. The Earth is going into one of these jumps, and you don't know what is going to be on the other side of those jumps. The Earth is always jumping. Things move on this planet. Things are not still. Everything is turning.
As it begins to run out of fuel, the sun won't simply fade away to nothing. Its core will collapse, and the extra heat this generates will cause its outer layers to expand. The sun is now dead. Its remains slowly cooling in the freezing temperatures of deep space. The fate of the sun is the same as for all stars. One day they must all eventually die, and the cosmos will be plunged into eternal night.
All stars eventually will run out of fuel. The temperature of the universe drops. The stars, one by one, in the night sky, will turn off. And there'll be no more new stars created. And so that the universe will end not with a bang, but with a whimper. And not in fire, but in ice.
With no fuel left to burn, a white dwarf's faint glow comes from the last residual heat from its extinguished furnace. Looking at it from where the Earth is now, it would only generate the same amount of light as the full moon on a clear night. The faint glow of white dwarfs will provide the only illumination in a dark and empty void littered with dead stars and black holes.
In some ways, it's kind of a ghost universe. It's the corpses, the zombie stars, that will take us into the future.
A black dwarf will be the final fate of those last stars. White dwarfs that have become so cold that they barely emit any more heat or light. Black dwarfs are dark, dense, decaying balls of degenerate matter. Little more than the ashes of stars. Their constituent atoms are so severely crushed that black dwarfs are 1,000,000 times denser than our sun. Stars take so long to reach this point, we believe there are currently no black dwarfs in the universe.
We have a pace of life that's based on really the energy available to us now. You could imagine living conscious systems which have a very different pace and therefore can extend out at least a lot farther than you'd imagine otherwise. You could have a living system where if it had a thought every 10 trillion years, that would seem normal. Even if our life dies out, one could imagine at some time arbitrarily far in the future, a fluctuation occurs which allows intelligent life to exist again for a little while. So you might have islands in time of intelligence.
Proton, one of the fundamental building blocks of atomic matter, of what makes us up, can just spontaneously fall apart.
Any material that evades the pull of a black hole eventually dies away. as its protons disintegrate.
The matter inside black dwarfs, the last matter in the universe, will eventually evaporate away and be carried off into the void as radiation, leaving absolutely nothing behind. With the black dwarfs gone, there won't be a single atom of matter left. All that will remain of our once rich cosmos will be particles of light and black holes. The arrow of time creates a bright window in the universe's adolescence, during which life is possible. But it's a window that doesn't stay open for long. As a fraction of the lifespan of the universe, as measured from its beginning to the evaporation of the last black hole, life, as we know it, is only possible for 1,000th of a billion billion billionth billion billion billionth billion billion billionth of a percent.
Black holes become the fundamental building block of the universe. A galaxy will basically be a supermassive black hole in a center with smaller black holes orbiting it.
Zombie galaxies filled with black holes continue to evolve.
They'll eat each other and they'll get bigger, and maybe they'll fall into the supermassive black hole and it'll get bigger. The universe will still be an exciting, dynamic place. It's just that the timescales you're talking about are now trillions of years instead of thousands or millions of years.
Black holes can bang on space-time like mallets on a drum. And they have a very characteristic song. Imagine two black holes that have lived a long life together. At the end of their lives, they're going around each other, crossing thousands of kilometers in a fraction of a second. As they do so, they leave behind in their wake a ringing of space, an actual wave on space-time. Space squeezes and stretches as it emanates out from these black holes banging on the universe. Those are the gravitational waves. They are literally the sounds of space ringing. And they will travel out from these black holes at the speed of light as they ring down and coalesce to one spinning, quiet black hole. If you were standing near enough, your ear would resonate with the squeezing and stretching of space. You would literally hear the sound. Imagine a lighter black hole falling into a very heavy black hole. The sound you're hearing is a light black hole banging on space each time it gets close. As it falls in, it gets faster and it gets louder.
Scientists used to think black holes were immortal, but even these will one day die.
Now we're talking about timescales of unimaginable length, quadrillions of years into the future. On that timescale, even the black holes begin to evaporate.
According to quantum mechanics, space is filled with virtual particles, antiparticles, that are constantly materializing in pairs, separating, coming together again, and annihilating each other. In the presence of a black hole, one member of a pair of virtual particles may fall into the hole, leaving the other member without a partner with which to annihilate. The forsaken particle appears to be radiation emitted by the black hole. And so, black holes are not eternal. They evaporate away at an increasing rate until they vanish in a gigantic explosion. Quantum mechanics has allowed particles and radiation to escape from the ultimate prison, a black hole.
Philosophers and poets have asked the question, will the world end in fire or ice? We can now give an answer. The latest evidence shows that the universe is not slowing down, but it's speeding up out of control. And the universe, we think, will die in ice. Trillions upon trillions of years from now.
Empty space itself has energy. In every little cubic centimeter of space, whether or not there's stuff whether or not there's particles, matter, radiation, or whatever, there is still energy, even in the space itself. And this energy, according to Einstein, exerts a push on the universe.
What is the weird stuff that's accelerating the universe? We call it dark energy. And this stuff is the dominant stuff of the universe. Almost 3/4 of the matter-energy content of the universe is this dark energy. And we don't know what it is.
Dark energy, unlike matter or radiation, does not dilute away as the universe expands. This has crucial implications for what the universe is going to do in the future.
So what will be the future of the universe? Well, if the dark energy remains dominant and repulsive, the universe will expand forever. Faster and faster and faster with time. A runaway universe.
70% of the energy of the universe resides in empty space, and we don't understand why. But we do know what will happen. If that energy continues to be there, the universe will become cold and dark and empty. That's the future as it might be. We don't know because we don't yet understand the nature of dark energy. Until we do, we won't know the future. We won't even understand our own origins, and that's why we want to know and study this subject.
Forecast does seem to be for an ever colder, ever emptier universe. But then, of course, we have to ask, could that end lead to a new beginning? And there are ideas whereby what actually is the end of our universe could in some sense be linked to the beginning of a new one.
We've worked out the mathematics, the equations. They seem to say that if you have an atom smasher that can concentrate tremendous amounts of energy at a single point, you can perhaps open up a gateway, a baby universe. Facing the death of everything there is, this perhaps is their only possibility of escape. And this also raises a very intriguing possibility, sheer speculation of course, that perhaps any universe that has intelligent life in it will create baby universes, will create lifeboats, and proliferate child universes. So an evolution may take among universes in the multiverse. Survival of the fittest may take place. So those universes which do not have intelligent life are infertile. They have no children. But those universes that have mild temperatures, stars like us, would create civilizations that could open up child universes, and they would then proliferate.
After an unimaginable length of time, even the black holes will have evaporated, and the universe will be nothing but a sea of photons gradually tending towards the same temperature as the expansion of the universe cools them towards absolute zero. Once the very last remnants of the very last stars have finally decayed away to nothing, and everything reaches the same temperature, the story of the universe finally comes to an end. For the first time in its life, the universe will be permanent.
In all of time, on all the planets of all the galaxies in space, what civilizations have risen, looked into the night, seen what we see, asked the questions that we ask.
What we see around us is staggering complexity. How is it possible? Living organisms are created by chemistry. We are huge packages of chemicals. Now, what are the ideal conditions for chemistry? Well, first, you need energy. But not too much. What you want is just the right amount, and planets, it turns out, are just right because they're close to stars, but not too close. You also need a great diversity of chemical elements. And you need liquids, such as water. Why? Well, in gases, atoms move past each other so fast that they can't hitch up. In solids, atoms stuck together. They can't move. In liquids, they can cruise and cuddle and link up to form molecules.
Liquid water is just so good for getting evolution going. Molecules can dissolve in the water, form more complex chains.
Now, where do you find such Goldilocks conditions? Well, planets are great. And our early Earth was almost perfect. It was just the right distance from its star to contain huge oceans of liquid water. And deep beneath those oceans, at cracks in the Earth's crust, fantastic chemistry began to happen. Atoms combined in all sorts of exotic combinations.
Microbes have adapted to survive the most hostile conditions. Arid deserts, the frozen Himalayas, in trenches under thousands of tons of pressure in the ocean deeps. In the vacuum of a space simulator, life forms have been flourishing for years without oxygen.
Very, very quickly, as soon as the Earth cooled off after its formation, we know that life began here.
because it happened quickly here on Earth, we think it's going to happen quickly on other planets as well.
We know that the galaxy is awash in water. It's awash in organic molecules and complex chemistry. All of the things that we know were necessary for life to begin on this planet exist in abundance throughout the galaxy. Did something similar to what happened on our own planet happen on those other planets?
There are more habitable Earth-mass planets in the observable volume of the universe than there are grains of sand on all the beaches on Earth.
just one bacteria on Mars, or any other body of the solar system, would indicate that the whole chain of evolutions, cosmic, chemical, and biological, is at work everywhere. In that case, the creation of life anywhere in the universe would be more the rule than the exception.
Within all of our lifetime, we're going to understand that there is life on other bodies in the solar system. We're going to understand the implications of that for evolution of life here on Earth. We're going to find planets around other stars that we can say we see potential signs of habitability in their atmospheres. That's all going to happen in the next 10 to 20 years. How exciting is that? We're on the verge of things that people have wondered about for millennia. Are we alone? And here we are on the verge of finding that out.
The universe is nearly 14 billion years old, and our galaxy is something like 12 billion years old. So there could be life out there that could be dramatically more advanced than the life that we have here on this planet.
The only elements that were created in the Big Bang were hydrogen, helium, and a little bit of lithium. All the stuff that makes your life livable, those elements weren't created in the Big Bang. The only place they were created is in the fiery cores of stars. And the only way they could get into your body is if the stars were kind enough to explode.
have any hope of finding alien life, we have to know what to look for. But where do we begin? How do we narrow down a seemingly infinite set of possibilities? There's one thing we know for sure. Nature will have to play by her own rules. No matter how strange alien life might be, it's going to be limited by the same physical and chemical laws that we are. On top of this, each alien environment will further limit what kinds of life forms can evolve there. Despite these natural boundaries, the possibilities are staggering to imagine. Trillions of planets, each a unique cauldron of chemicals undergoing their own complex evolution. To guide our thinking, this museum of alien life will be divided into two exhibits. Life as we know it, home to beings with biochemistries like ours, and life as we don't know it, home to beings that challenge our concept of life itself. Before we venture too far into the unknown, we have to ask ourselves, what if alien life is more like us than we think? If there's one feature that unites us with the other specimens in this museum, it's carbon.
Carbon is ubiquitous. It's one of the most common elements in the universe, and it's very good at forming large, stable molecules.
Carbon has the rare ability to form four-way bonds with other elements and to bind to itself in long, stable chains, enabling the formation of huge, complex molecules. This versatility makes carbon the centerpiece in the molecular machinery of life. And the same carbon compounds that we use have been found far from Earth, clinging to meteorites, and floating in far-off clouds of cosmic dust. The building blocks of life, drifting like snow through the universe. And if alien life has selected other carbon compounds for their biochemistry, they will have plenty to choose from. Scientists recently identified over 1 million possible alternatives to DNA, all carbon-based. If we ever discover other carbon-based life forms, we would be fundamentally related. They would be our cosmic brethren. But would they look anything like us? If they hail from Earth-like planets, we could share even more in common than just our biochemistry.
What would life be like on other planets if it has evolved? Would it be like the world today here on Earth? Or would it be completely different? There are those who argue that from the argument of convergent evolution, if conditions on other planets are similar to here, then we would see very similar life forms. Animal and plant-like organisms that look very familiar.
On Earth, certain features like eyesight, echolocation, and flight have evolved multiple times independently in different species. This process of convergent evolution could extend to alien planets like Earth, where creatures face similar environmental pressures. It's no guarantee, but there could be certain universalities of life. The greatest hits of evolution on repeat across the universe. Each feature would be attuned to its local environment. Dimly lit planets would produce huge eyes to suck in extra light, like nocturnal mammals.
Some people have gone so far as to say that human-type organism, humanoids, will occur on other planets.
The existence of other human-like organisms seems unlikely, given the long, convoluted chain of events that produced us. But we can't rule it out. If just one in every 100 trillion Earth-like planets produced a human-like form, there could still be thousands of creatures like us out there. Convergent evolution is also rampant in plant life, and C4 photosynthesis has arisen independently over 40 times. Would alien plants look like ours or something else entirely? On Earth, plants appear green because they absorb the other wavelengths in the sun's light spectrum. But stars come in many colors. And alien plants would evolve different pigments to adapt to their sun's unique spectrum. Plants feeding off hotter stars could appear redder by absorbing their energy-rich bluer light. Around dim red dwarf stars, vegetation could appear black, adapted to absorb all visible wavelengths of light. Earth itself may have once appeared purple due to a pigment called retinol that was an early precursor to chlorophyll. Some think that retinol's molecular simplicity could make it a more universal pigment. If so, we may find that purple is life's favorite color. Vegetation is more than just a curiosity. It's chemical information that could be seen from light years away. Earth plants leave a signature bump in the light reflected off our planet. Finding a similar signal from another world could point the way to alien vegetation. Perhaps this will be our first glimpse at alien life, a vibrant hue cast by a distant world.
What happens when you change the day length of a planet? What happens when you change the tilt of a planet? What happens when you change the shape of the orbit? What happens when you change the gravity of a planet?
Planets with long elliptical orbits would see drastic seasons. There could be worlds that appear dead for thousands of years, then suddenly spring to life. Most of the rocky planets discovered so far have been massive super-Earths. How would life evolve on these worlds? In the seas, gravity may not matter much at all.
A high-gravity planet isn't high gravity all over. If you're in the sea, and that's where all life starts, there's very nearly no gravity because you're much the same density as the stuff around you. It's when the animals come out on land that they feel the gravity.
High G-forces would necessitate large bones and muscle mass in complex life on land. They would also demand a more robust circulatory system. And plant life could be stunted by the energy cost of carrying nutrients under stronger gravity. Low-gravity planets would more easily lose their atmospheres to space and lack a magnetic field to protect from cosmic rays. But smaller worlds could be home to secret oases. Huge cave systems that provide hideouts for life. Possible habitable planets are estimated at 2.5% Earth's mass. If surface life does evolve on these worlds, it could be a sight to behold. Plant life could grow to towering heights, able to carry nutrients higher in lesser gravity. Without the need for bulky skeletons and muscle mass, animals could have body types that boggle the mind. Here on Earth, it took 3 billion years for evolution to produce complex plant and animal life. Simpler organisms are hardier, more adaptable, and more widespread. The largest collection in the Museum of Alien Life would likely be the Hall of Microbes. Yet finding even the tiniest alien microbe would be a profound discovery. bite-sized life could leave a big footprint. Like stromatolites on Earth, layers of microbes could build up into huge rock mounds over time, leaving behind eerie structures. And in big enough numbers, some alien bacteria could leave a distinct biosignature by exhaling gases that wouldn't coexist naturally, like oxygen and methane.
There's ways to make oxygen without life, there's ways to make methane without life, but to have them in the atmosphere together is almost impossible unless you've got biology making those gases at the surface. And it would have an imprint on the planet's spectrum of colors.
Next generation space telescopes could find a signal like this on a world not far from home.
The closest sun-like star with an Earth-like exoplanet in the habitable zone is probably only 20 light years away and can be seen with the naked eye.
Most brown dwarfs are too hot to support life as we know it, but some are just cold enough. All the prime elements for life have been detected inside their atmospheres. And within these clouds, some layers would provide ideal temperatures and pressures for habitability. There could be photosynthetic plankton in these skies, kept aloft by churning upwinds. And with enough force, these upwinds could even support larger, more complex life. Predators. This raises a crucial question. What if we've been looking in all the wrong places? What if nature has other ideas? Most of the universe is too cold or too hot for liquid water and the biochemistry that supports life as we know it. But in case our biases are misleading, we have to cast a wide net to search for life outside the habitable zone, in places that seem wildly hostile to us. Exotic environments will demand exotic biochemistries, and while no element can match carbon's versatility, one contender is a frontrunner. At first glance, silicon seems similar to carbon. It forms the same four-way bonds and is also abundant in the universe. But a closer look reveals that these two elements are false twins. Silicon bonds are weaker and less prone to forming large, complex molecules. Despite this, they can withstand a wider range of temperatures, opening up intriguing possibilities.
Life based on the silicon atom instead of carbon would be more resistant to the extreme cold, providing a whole new range of weird forms.
But silicon has a problem. In the presence of oxygen, it binds into solid rock. To avoid turning to stone, silicon beings might be confined to oxygen-free environments, like Saturn's frigid moon, Titan. Its vast lakes of liquid methane and ethane could be an ideal medium for silicon-based life or other radical biochemistries. Without ample sunlight, beings on worlds like Titan would likely be chemosynthetic, deriving their energy by breaking down rocks. Such life forms could have ultra-slow metabolisms and life cycles measured in millions of years. In high temperatures, typically rigid silicon-oxygen bonds become more flexible and reactive, triggering more dynamic chemistry. This has led to a truly bizarre proposal: silicon-based life forms that live inside molten silicate rock. In theory, these forms could even exist deep beneath the Earth inside magma chambers as part of a shadow biosphere. If so, then the aliens are right under our noses. Other shadow biospheres have been proposed, forms of life living alongside us that we don't even know are here, including tiny RNA-based life small enough to go undetected by existing instruments. Clouds of dust in empty space might seem like the last place you'd expect to find anything living. But when cosmic dust makes contact with plasma, a type of ionized gas, something strange happens. In simulated conditions, dust particles have been seen spontaneously self-organizing into helical structures that resemble DNA. These plasma crystals even begin to exhibit lifelike behavior, replicating, evolving into more stable forms, and passing on information. Plasma is the most common state of matter in the universe. If complex evolving plasma crystals really exist, and if they can be considered life, they could be its most common form. massive suns explode, some collapse into ultra-dense cores called neutron stars. Hulking masses of atomic nuclei crammed together like sardines. Conditions on the surface are mind-boggling. Gravity is 100 billion times stronger than Earth's. But beneath their iron nuclei crust lies something strange. A hot, dense sea of neutrons and subatomic particles. Stripped of their electron shells, these nuclei would obey entirely different laws of chemistry, based not on the electromagnetic force, but the strong nuclear force which binds nuclei together. In theory, these particles could link up to form larger macronuclei, which could then combine into even bigger supernuclei. If so, then this bewildering environment would mimic the basic conditions for life: heavy nucleon molecules floating in a complex particle ocean. Some scientists have proposed the unimaginable: exotic life forms drifting through this strange particle sea, living, evolving, and dying on incomprehensibly fast timescales. Life is not something that has to evolve naturally. It can be designed. And once intelligence is introduced into the evolutionary process, a Pandora's box is opened. Typical biological limitations, synthetic and machine-based life could be the most successful of all. It could thrive almost anywhere, including the vacuum of space, opening up vast frontiers unavailable to biological organisms. And compared to the glacial pace of natural selection, technological evolution allows exponentially faster growth, adaptability, and resilience. By some estimates, autonomous self-replicating machines could colonize an entire galaxy in as little as 1 million years. Can't predict how hyper-intelligent life would organize itself. But in theory, there could be convergent evolution at play. The electrical properties of silicon might make it a universal basis for machine intelligence, a redemption for its biological shortcomings. ages, perhaps machine intelligence will come to dominate, and naturally occurring biological life will be viewed as a quaint starting point. Perhaps we ourselves will lead this transition, and the great human experiment will be merely a first link in a sprawling intergalactic chain of life.
Isley has said that one does not meet oneself until one catches the reflection from an eye other than human. One day that eye may be that of an intelligent alien. And the sooner we eschew our narrow view of evolution, the sooner we can truly explore our ultimate origins and destinations.